Alright, so we're going to look at an inquiry lab on 3D figures. Hopefully at this point you have at least a little bit of background. I'm sure you've worked with prisms and pyramids before, which was kind of the hope going into this, is that you're going to use your background knowledge of both three-dimensional figures that you've seen already, prisms and pyramids, and also area of two-dimensional shapes, rectangles, squares, circles, specifically triangles also, to be able to move on and do these types of problems. So the goal of today is to walk away with a good understanding of the basics of three-dimensional figures that maybe you're a little bit less familiar with, so that going into lessons 1 and 2 especially, you're going to be able to have a lot of success. So we're looking at how are some three-dimensional figures related to circles. Okay, so hopefully the basketball court activity was helpful to you when we found the area of some circles. We actually also found the area of a semicircle, a couple of different sizes there. Main idea being that to find the area of a circle, you have to take the formula pi r squared, where r is the radius, in order to calculate that value. So here's what we're looking at. This guy's name is Kenji. That's an interesting name. He's training his dog to run through an agility course. One of the activities in the course is the tunnel, an open tube through which the dog runs. I don't know if you've seen these on TV or anything, but maybe you have some of this stuff at home. If you have like a one of those foldable tunnel situations. We have one for my kids. They haven't used it in a while because they've kind of outgrown it a little bit, but you get the idea. It's going to be a cylinder-shaped situation. So first of all, we're going to investigate. A three-dimensional figure with faces that are polygons is called a polyhedron. Okay, polyhedron. There are three-dimensional figures that are not polyhedrons as well. Some examples of these figures include cylinders, cones, and spheres. So we're going to be talking about cylinders, cones, and spheres today. Those are not polyhedrons. First, let's do a little bit of brainstorming. Hopefully you have some familiarity with real-world type objects that would represent each of these shapes. Just kind of thinking of some different things. Cylinders, most people think of some kind of can, whether it's a can of soda, a can of soup, you get the idea. Definitely any type of can would be applicable there. For those of you who eat oatmeal, have you ever seen those oatmeal canisters? Whether it's Quaker Oats or whether it's whatever kind of oatmeal you eat, you know what I'm talking about. You have the oats inside the container there, and it is also a cylinder shape. It has a lid on the top. Coffee containers, very similar. And shout out to Mr. Jazak. You guys who are in science, you have something called a beaker, and it is a glass container that you can pour liquid into, and it generally looks like a cylinder. It has a little spout at the top usually, but it's somewhat of a cylindrical shape. For cones, obviously the most common that people think of would be an ice cream cone. And now these are, they're obviously two different types of cones you're probably familiar with. One is like the light tan colored, and it's sort of like the consistency of a Rice Krispie. It's crunchy, but it's light and kind of air-filled. You also have what's called a sugar cone, if you're familiar with this, or a waffle cone, one of the two, where it kind of basically looks like a rolled-up waffle, and it's crunchier, I suppose, and that's kind of what we're talking about here. You also have something, I don't know if you've used this, if you like to experiment with cars or anything like that, or even different things in the kitchen, you use a funnel, and that helps you if you're trying to pour liquid from one container into another, and the openings aren't quite beneficial for that. In other words, you're trying to pour like a gallon of milk into a very, very small container, or a container with a small opening. You would use a funnel and pour the liquid into the funnel so that you don't spill, and it goes right into the container that you're trying to pour into. And then obviously agility cones, traffic cones. If you think of those big orange cones that you see here, there, and everywhere outside, especially during construction season, which basically is any season but summer. Traffic cones or agility cones or whatever. So you know what those look like. The big black bottom, orange at the top, hole at the top, and at the bottom. You get the idea. So those are real world examples of that. How about spheres? Basically any type of ball. We'll say basketball because that happens to be on a lot of our minds lately, what with March Madness and the girls' season ending and the student staff game and all that wonderful stuff. A basketball is definitely a sphere. How about the planet Earth? Sphere shape. There's certainly flat Earth debaters, but I think that has kind of been myth busted, so to speak. And the last one that we're going to consider with little kids, especially nowadays, as the weather starts to get nice, we go outside and we blow bubbles. So those are also sphere in shape. Hopefully that gives you, an idea of some real-world examples of these three-dimensional figures. So the important thing here to recognize is that if you consider, let's take a rectangular prism and a rectangular pyramid. They both have a base, right? The base is the bottom. And in terms of if I were to draw, no, they don't have, well, maybe they do. Let's see. No, they don't have one. At any rate, if I was going to draw, let's say, a rectangular, use the pen, rectangular prism. It's basically a rectangle, and then I have my three-dimensional situation here where I've got the sides on the back. I don't usually draw the dotted lines unless it's absolutely necessary. So here's a prism, rectangular prism. And then if I wanted to draw a rectangular pyramid, the only difference is still going to have this situation on the bottom. It looks like a parallelogram, but that's just based on perspective. Okay? And then I do my top here, and I basically connect the sides that are visible. This side would be connected on the back side. In fact, just for all intents and purposes, we'll just do the dotted line coming up the back. This would look something like this. There you go. Now it's see-through. So there's your prism. Here's your pyramid. And you get the idea that the thing that we're calling the base, first of all, if I have a prism, then I have two bases, right? Okay, this rectangle. It really doesn't matter which rectangle it is. And then you have this rectangle on the bottom, the one that the pyramid is laying on. It's technically a square if you want to get technical about it. You can also have a rectangular pyramid, which would be a rectangle. The sides of the triangles would be different, but you get the idea. Okay, so just as a rectangular prism and pyramid have bases, in this case rectangles, cones and cylinders have bases as well. So if you consider this base right here and this base right there, what do they look like? They look like circles. Exactly. So the base of a cylinder is a circle, and the base of a cone is a circle. Good information to have, because you can do a lot of things based on that knowledge moving forward. Okay, so they're both circles. You can also do what's called taking a cross section. A cross section is a two-dimensional representation anywhere along the shape. So this green two-dimensional it'd be like taking a piece of paper or a knife or a razor blade or something and cutting through two-dimensionally, if you can imagine that. And it says, interesting shapes can occur when you find the cross-section of a figure that is not a polyhedron. Describe the shape of the figure resulting from a horizontal cross-section of each of the following. So if I stick like a piece of paper or a razor blade through a through a cylinder, my mistake, through a cylinder, the result is going to be this two-dimensional shape right here, which obviously looks a lot like the base from up here. And you guessed it, the cross-section is going to be a circle. What about if I take a two-dimensional cross-section of a cone? Well, you can kind of tell that it's still going to be a flat two-dimensional surface. It looks a little bit smaller than the bottom one, but it is still going to be a circle. Believe it or not. And then how about a sphere? Again, anywhere you cut this thing, the size is going to change a little bit, but no matter where you cross-section a sphere, that two-dimensional resulting shape is also going to be a circle. So you'll notice that as we move along, cylinders and cones and spheres have a lot of common characteristics, and that's based on the fact that the cross-section is a circle. It's also based on the fact that the base of these two shapes is a circle as well. Okay? Pause anywhere you need to pause. If you need to go back and look at any of that information again, please do so. Otherwise, we are moving on to the next page. Work with a partner. Guess who your partner is? We've done this enough times. Draw and describe the shape resulting from each cross-section. Okay, this is going to be a little bit challenging, so I'm going to need you to kind of think outside the box a little bit. And what we're going to do is, first of all, identify what the yellow or tan, whatever color you think that is, orange shape is, the three-dimensional solid. And then based off of that, we can look at how it is being cross-sectioned and determine what the two-dimensional result is. Okay, so you've seen those magic tricks. In fact, I think we were just talking about it the other day, where the magician has an assistant go into a box, and they kind of cover up the middle of the body, and it looks like the head is sticking out and the feet are sticking out, and then they put those huge blades through there, and it looks like they're cutting through the person's body. That's kind of the idea here. Okay, so if you want to think of that kind of an interesting far out example, but you get the idea. At any rate, the difference between this cross-section and the one from the previous page is the angle at which I'm being cross-sectioned. Okay, on the other side, I cut through completely perpendicular to the height of the cylinder. Okay, so what I mean by perpendicular, obviously, is it goes straight across and makes a 90-degree angle with the height. This is not perpendicular, right? It's kind of at an angle, so it's going to change the resulting shape. And I don't know if you can envision this, imagine this, but if you did this, the result would be not a circle, but something that's kind of egg-shaped, okay? And the idea here is that it's an oval. It's more of an oval shape than a circle. On the previous page, we did cross-section a cone, except we cross-sectioned it this way, going across, right? And we came up with the fact that it's a circle. What if you cut it down the middle vertically like this? If you can imagine what's going to happen, you have this straight side going across the bottom, you have an angled side going up like this, and you have an angled side going up like that. What does that look like? Hopefully, it looks like one of these. And that's exactly what happens when you vertically cross-section a cone, is you get a triangle. So you basically have a circle on the bottom and then a triangle two-dimensionally if you stood it up flat like that on top. This is a sphere, and we took a horizontal cross-section. This is kind of diagonal. It really makes no difference how you cross-section a sphere. You are always going to get a circle of some kind. Now this happens to be, I believe the example on the other page was right at where the radius would be, right through the middle, the geometric center of the shape. This one appears to be about the same, except it's on an angle instead of horizontally across. But again, no matter what, you're going to have different sizes depending on where you cross-section the sphere. But no matter what, the result is going to be a circle. This one's kind of tough, number 4. In fact, we're going to skip it and come back to it right now. Number 5, the three-dimensional shape. It's also a sphere. I know it's kind of difficult to tell, but the idea here is that it's a sphere. So again, now we're cutting it vertically. And if you recall, we mentioned that the result, no matter what, consider what you did for number 3, the result, no matter what, is going to be a circle. So this is going to be the exact same shape, no matter what. You cross a section, a sphere anywhere, the result is a circle. So let's skip ahead then to number 6. Again, you kind of have to use your imagination. Remember, this is a cylinder. If I horizontally cross-section a cylinder, I get a circle. If I cross-section it kind of on an angle like I did up here, I'm going to get an oval. Well, what happens if I cross-section it vertically, completely vertically? That takes the circle part of it out, really. So I don't know if you can picture this or not. Hopefully you can. So I've got a straight edge on this side, I've got a straight edge going across, I got a straight edge coming down, and I got a straight edge coming across. This, in fact, is, you guessed it, a rectangle. Okay, so if you're thinking in terms of cylinders, this actual cross-section is going to be a rectangle, and that's helpful going forward as we start to calculate area to be able to determine what two-dimensional shapes make up these three-dimensional solids. So let's get back to number 4. This is, if you have a certain amount of mathematical experience, this may or may not make sense to you. So here's this situation right there, right? And most people would forget about the bottom, the fact that it comes all the way across. So your first glance would be like, oh, well, it's a half circle, okay? Or even maybe like a half oval. And if you said that, technically, if you said like half oval, you'd be correct. Here's the deal. This two-dimensional situation, and as you progress through mathematics, you'll learn a lot more about these. This is what we call a parabola. And if you have any understanding of graphs, you have probably seen a parabola before, especially if you're an algebra student. A parabola is basically the graph of a function to an exponent of 2. So if I had something like y equals x squared, I believe regular math students have had this too. It's the curve U shape, right? That's a parabola. So that's basically what we have if we cross-section this figure here. We get a parabola. So I'm not going to spend too much time on that. You can kind of use your own background information in those areas, but I just want to kind of highlight. There's your circle. Here's your triangle right there. There's your oval shape, kind of tough to determine two-dimensionally. There's your circle. Again, perspective is everything. And we see the rectangle there, okay? So again, if you need to review any of that, please do. Otherwise, let's move on to our reflection statements. True or false? The cross-section of a cylinder, a cone, and a sphere will always be a circle or an oval. Always? No, not always. Why? Give a counterexample, it says. Well, there's one up here. This is not a circle, right? Nor is this a circle. So it says the cross-section of a cylinder, a cone, and a sphere will always. If false, provide a counterexample. Well, it is false. The counterexample is that a vertical, right, because we took a vertical cross-section, straight up and down, all we have to do is provide one counterexample, by the way. A vertical cross-section of a cylinder, that's what we did right here, is a rectangle. And there's my proof right there. So maybe I'm going to put number 6 in parentheses to remind myself, hey, number 6, that's a cylinder. The vertical cross-section is a rectangle. So no, it is not always a circle. And so then my final question, how are some three-dimensional figures related to circles? Well, first of all, from a standpoint of cones and cylinders have a circle base. That's definitely something you want to mention. And then what about spheres? We don't have a whole lot of experience with spheres, but a sphere is essentially what? It's essentially a 3D circle. I know that may not make sense, but think about a basketball, or it is a circular shape. If it was flat, if you looked down on it from above, or if you looked at it sideways, it would look like a circle. So it's basically a 3D circle, right? So that's how those different shapes are related to circles. Cylinder and a cone both have a circular base. Also, if you take the horizontal cross-section, which would be parallel to the base, those would also be circles. And then a sphere is basically a three-dimensional circle shape. So hopefully you will find this background information helpful to you. I can tell you that Lesson 1 and Lesson 2 focus on the volume of the first two shapes that we talked about, which are cylinders and cones. There isn't a whole lot to do besides memorize formulas, because that's kind of the focus of geometry, and then be able to apply those formulas into various situations. So again, hope this was helpful. If you need to review any of this, please go back and do so. Otherwise, make sure that your name is on the front of this page. Tear it out, turn it in, and you are done with this activity. Thank you for your time.